Hello, ladies and gentlemen. My name is Georgios Christou, and I'm a research assistant in the Institute of Structural Concrete in the University of Aachen. Thank you for attending my presentation today, in which I will be showing some research results regarding concrete fatigue of composite constructions with rib shear connectors. I would like to begin my presentation with a small introduction regarding the advantages of rib shear connectors. Let's take a look at the results of our static reference test consisting of a single rib shear connector. While these dowels offer high load-bearing capacity and an initial stiffness, which is also very high, they are also ideal in case of cyclic loading because of their weld-seam-free construction. The research issue of our work was the behavior of these connectors under cyclic loading, such as cyclic stiffness, cyclic slip increase, and static stiffness over the lifespan, and the fatigue failure of the concrete. For the investigations of local effects, we chose a modified single push-out test. While in typical push-out tests, as suggested in Eurocode 4, shown in the upper left corner of the slide, the forces are distributed unevenly in the dowels. In single push-out tests, the force is introduced in just one dowel, thus providing precise characteristic dowel curve. The previously used single push-out test rigs, as shown in the lower left section of the slide, had the disadvantage of an eccentricity due to the shifted lines of action. The latter led to fatigue of the test rig and premature termination of the test. Thus, a new modified single push-out test was created, as shown in the middle, in which the lines of action were identical and the test rig was designed with a very high resistance against cyclic loading. In the series of the single push-out tests with the new test rig, we were able to reach up to 10 million load cycles. In our tests, we measured the slip, the rotation of the dowels, and the steel dowels movement against the steel web by means of 5 inductive displacement transmitters. Further advantages of the new modified single push-out tests are that our concrete slabs were relatively small and thus we had an ease of use. We had no inclination of the concrete slab as measured by the displacement transmitters, and we have a clear distribution of forces. Additional to the single push-out test, we performed girder tests with a slim girder as seen in the section. The geometry of the dowels and the concrete cover were chosen identical to the ones of the single push-out tests. In our girder test, we measured the slip over the length of the girder as shown by the red inductive displacement transmitters over the length of the girder. We measured the deflection and the elongations of the concrete and steel over the height of the girder. The test program for both the single push-out tests and for the girder tests consisted of an initial static loading to the upper load, 100,000 load cycles, and a relief of the load, after which we started over. The latter allowed us to capture the evolution of the static stiffness of the specimen over the lifespan. The load parameters were chosen with the criterion that the shear forces per dowel in the girder shall be equal to the ones we used or chose in the single push-out tests. The upper load per dowel was chosen to 225 kilonewtons and the lower load to 150 kilonewtons for the single push-out test and 140 kilonewtons approximately for the girders. For reference, we can take a look at the load-bearing capacity of the used dowels as per the current technical approval in Germany. The chosen upper load amounts to approximately 190 kilonewtons per dowel in the characteristic level, and we can see that our chosen 225 kilonewtons are approximately 80% of the calculative mean load-bearing capacity, which is approximately 280 kilonewtons. The actual load-bearing capacity as per the static reference tests was approximately 380 kilonewtons. Regarding cyclic loading, the current technical approval suggests a restriction of the upper load at approximately 70% of the characteristic load bearing capacity, and a further restriction regarding multi-axial concrete damage, which is in our case approximately 150 kilonewtons. Since we were interested in fatigue failure, which shows particularly high loads, a further increase of the upper load would lead to steel girder reaching the yield strength and was thus not possible in this case. If we now take a look at the results, we can see on the left side of the slide the slip in several sections of the girder for several timeframes between 0 and 2.0 million load cycles. As expected, the slip increases over the lifespan of the test. The slip increase ratio is very high in the first 100,000 load cycles, and after that, the ratio of the slip increase declines constantly. After approximately 1.5 million load cycles, the slip increase is almost negligible. The deflection of the girder shows the same principle. While in the beginning of the test the deflection increases significantly, we observe a very slow further increase of the deflection after approximately 0.5 to 1.0 million load cycles. Comparing the slip of the girder with the slip of a single push-out test, we can observe very similar results in case of the most loaded dowels of the girder. The slightly higher slip, which is reached in the dowel of the girder, can be led back to our simplified load determination in which we assumed an equally distributed shear force over all dowels within the shear fields of the girder. The force per dowel is actually affine to the slip in the interconnection, which leads to unevenly distributed shear forces in each dowel of the girder, at least in the beginning, before the occurrence of high inelastic slips. Thus, the observed dowel near axis N is subjected to higher forces than the ones assumed. As the inelastic slip increases, the shear forces are redistributed, and the shear force near axis N decreases slightly as more load cycles are introduced. After the first fatigue phase is completed, in which significant slip increase is observed, the forces in each dowel can be assumed to remain constant and roughly equal over the length of the girder. It is important to notice that according to the static reference test, a slip of approximately 1 millimeter is needed to reach the upper load of 225 kilonewtons per dowel, while the stiffness of the dowels reduces after that significantly. By means of the elongations measured over the height of the girder, it is now possible to calculate the shear forces which are transferred between the sections. These measurements were performed in every fourth dowel over the length of the girder, for example in axis C, axis E, and axis G. Although the dowels provide theoretically a full shear connection, the assumed rigid connection of the composite partners is invalid from the beginning of the test, since slip is required to activate the dowels. This can be observed comparing the elongations of the steel and concrete near the lower surface of the concrete, where a gap is observed between the steel and concrete strain, as seen here in the example of axis G. By means of the elongations measured over the height of the girder, the shear force per dowel was now calculated, and considering the slip in the interconnection, it is possible to calculate the cyclic dowel stiffness of the dowels and compare them to the stiffness of the single push-out tests. Once again, we have a very good agreement between the single push-out test and the girder test. The roughly constant cyclic stiffness in combination with the roughly constant elastic slip in the interconnection suggests a constant loading over the lifespan of the girder as soon as the first fatigue phase is completed. In summary, we have seen a very good load-bearing behavior under the cyclic loading. We could not observe any failure. Fatigue of concrete as well as fatigue of steel lead to degradation of the composite joint. Yet we did not have a clear failure besides slip and deflection increase. The failure criteria regarding load-bearing capacity under cyclic loading in the current technical approval are very conservative, and fatigue together with creep might lead to serviceability limit state being decisive. In the future, we need more experimental investigations in order to further analyze the fatigue failure of the concrete. For example, in girders with partial connection, in which we might reach higher loading of the single dowels. Moreover, the design in case of fatigue shall be rethinked. For example, we might be able to use the mean value level of the load bearing capacity of the dowels instead of the design level. Thank you very much. I would be pleased to answer some questions.